So vector equations for a line can be very useful. You probably use GPS on your phone. I'm sure you're a modern human being. GPS use approximately 30 satellites orbiting the Earth. Whatever your location is, at least 4 GPS satellites are visible at any time, and each satellite sends out information at regular time intervals about its position. Your GPS device receives these positions and calculates how far it is from each satellite. Your GPS device requires information from at least 3 to identify your location. That's triangulation or trilateration. You can watch the video in section 5.3.0 if you want to know more about it. Data can be used to plot vectors and represent the movement of the Earth's tectonic plates so as to predict the likelihood of earthquakes. You can read about this in that article. In this subtopic, you will learn how to use vectors to form alternative versions of equations for a straight line that we will see you can apply in kinematic problems next week involving motion of a straight line. Different representations of lines help us analyze different aspects of directional motion. Under what circumstances might a vector equation be more useful than a Cartesian equation? Honestly, motion equations. What information does it give? What extra information? You'll kind of see that later. It's a little easier than three-dimensional. And it's probably generally an easier way than 3-variable systems. Theory of knowledge. Writing lines in various forms could be considered a type of model. They should probably be considered a type of model. Models are important in knowledge production in all areas of knowledge because they serve to represent knowledge. Key knowledge issue with models, however, is their simplified representations of a thing, not the thing itself. So the knowledge question is, do mathematical models hold a higher level of validity than models in other areas of knowledge? And that would be something you could discuss in theory of knowledge class. So the vector equation for a straight line. Right? So what vectors do is instead of slope, you're using components. So instead of a slope of 1/2, we'd write that as a vector of 2, 1. And so you're probably used to y equals mx plus b. Or in this case, if a lot of times they'll do b plus mx. So the vector equation for a line becomes some point. It doesn't have to be a y-intercept point. Plus and you can easily expand this with the vector to 3 dimensions by just going x, y, z. So it's like somewhere down here, they're going to notate it. And they're going to show this with all these vectors going from the origin. And they're going to let it lead to this, which shows up in a later section. basically showing that all of these equal a constant lambda. The change in vectors. But this really simplifies out into this. This is your simplified version of the vector equation for a line. The R vector, and make sure when you write it, you write R with the vector over it. I think I failed to do that in the next video, but as this is my initial point, or like my point and point slope. This is my three-dimensional slope or change vector. So write a vector equation for a line passing through the points 1, 1, 1 and negative 1, 2, 3. So I would say the easiest way to do this is I'm just going to do 1, 1, 1 as my initial point. And then, yes, doing plus b minus a lambda b minus a. Negative 1 minus 1 is negative 2. 2 minus 1 is 1. 3 minus 1 is 2. There's my vector equation for a line. Lambda is just a scalar. When you often it'll be t.
Point, but you're giving point on the
Mm-hmm. Yes, any point on the line. So, so C is the point 2, negative 2, 2. Use your answer in part A to determine if A, B, and C are collinear. So what I'm going to do is plug it in for a point, see if it's on my line, see if there's a common lambda. Which effectively I'm going to do these one line at a time. So the first line, and I'm going to label this line 1, I get negative 1/2. So I'm going to try that on line 2. That's not true. So I'll leave that for a second. If line 2 was true, I would need to test line 3.
line.
So line 1, I just solved. It said, where are the x's going to be? Essentially, what lambda would give me equal x coordinates. And then I tested if that lambda would also give me equal for y. That makes sense how I got that. So I took line 1, 2 equals 1 plus lambda times 2. To get the first equation, it's a different color. I'm taking line 1, lambda times that. Two is there on all of them. Yep. So they tend to show out all of them, and they got three different ones. I think as soon as you've got two, you know they're not collinear. Why did? Because I knew -1/2 was where it was for the first one. If you want, you can do it how the book did it, which is just solved it. That's correct. So they solved all of them and got three different values, which tells you that it's not a single lambda, so they do not inter they're not collinear in this case. You might also see this equation. This is kind of a useful thing to note. This equation can be written like this. So they just put them in a single line. And that can be helpful to do. Common lambda. Yep. There's a few different ways to do it. I don't know. Right now, I feel like finding one, plugging it in, see if it works. But checking. And as soon as you get one that's two of them that are not the same, you don't really need to check the third one. Okay, find the vector equation for the line containing these 2 points. Start with it. Yeah, I'm gonna do, I guess, AB vector. Probably shouldn't have labeled that how I did. The AB vector is the difference. So we're gonna do from A to B is B minus A is 10. 2 to -2 is -4. -1 to -7. No, it doesn't just want the vector, but that's going to be my thing that I multiply by lambda. A starting point. So the vector is that's the change vector or the slope vector, essentially. One, two, -1. No. And -4, -6. I put the lambda behind this time instead of in front. Okay, show that S lies on the line and T does not. So -14 equals 1 plus 10 lambda. That's going to be -1.5. I'm going to call that L1. Line 2, 8 equals 2 minus 4 lambda. And I get 6 equals -4 lambda. Lambda equals -1.5. L3. Add 1, 9 equals -6 lambda. So yes, that one does work. And then I do the other one. This is an L1, line 2, of it -7. And here, these two are not the same amount. Well, they're finding the third one. So that T is not on the line S, they were all the same, so S is on the line. Write the equation for a line that passes through D and is parallel to this vector. Parallel vectors all have the same essentially slope or direction vector. This is really, really easy. So D is my point. Direction vector, 2, -3. We didn't have to subtract because it gave me a direction vector instead of 2 points. It's like that's quite a bit easier than the last few. It's just a translation. And vectors have no position, so all vectors with the same direction are parallel and are essentially equivalent. Find a vector equation for a line passing through these two. Hence, find the possible coordinates of point R on the line that satisfies KR equals 3RL. Okay, we'll have to figure that out later, but vector equation for a line. Little r. The change from 1 to 0 is -1. From -1 to 0 is +1. From 1 to 2 is 1. So KR equals 3RL. So there's my line. That's what we have. Oh, okay. Distance from K to R. So they're taking the vector equation for a line and subtracting from K. So 1 minus lambda, -1 plus lambda, and 1 plus lambda. That's my vector equation for the line. Minus K. K was the point 1, -1, 1. Equals 3. That was the point R, or KL.
What? Remember what the question is.
So let's look back. So here's our 2 points, K and L. And we're supposed to show that KR equals 3 minus RL. And KR is the line. For R, we're using the line. And you always do second minus first.
Wait, R or
No, R is a point. We made the equation for the line. We know R is on this line. And when we find like how so it says find the vector equation for the line. We did that. And assign the possible points of point R, which is on the line. Is on the, what's on the line through KL. There's a line that goes through them, little r goes through them. And there's as r is on little r, and it has to satisfy this equation. And we know that when we do vectors, we do second minus first. So that becomes, so we're going to do L minus little r. This is a challenging problem. So minus K. And so we're going to start, I'm going to just put this together. 1 minus lambda minus 1 is just negative lambda.
Why did we do L minus?
Why did we do L minus K? So KL means L minus K. So the equation was KR, so I had to do R minus K, and then RL, which told me I had to do L minus R. So I had to switch the order of what I'm subtracting here. So this is just a demonstration of how and we did that when we found this vector.
R. Little r.
Little r is going to the lambda values. So right now I'm simplifying this. 1 minus lambda minus 1 is just negative lambda. Negative 1 plus lambda minus negative 1 is plus 1, just lambda. 1 plus lambda minus 1 is lambda. And then if you simplify this, you get 1 minus lambda, 1 minus lambda. Oh no, you get negative 1 plus lambda. So I've got 3 on the outside. Negative 1 plus lambda. Positive 1 minus lambda. 2 minus 1 is 1 minus lambda.
L minus.
And then they multiply the 3 through and get this. Then if we take line 1 and solve for lambda, we get lambda is 3/4. You should get that for all of them. To get, what does it ask me for actually?
What R?
I think it wants R. And so they do OR, which is, yeah, then they plug in 3/4 into this vector, into the R equation, and solve, because that's lambda. So lambda was 3/4. Now we're taking our lambda of 3/4, plugging it into that, to my line equation. 1 plus 3/4 times negative 1 is 1/4. Negative 1 plus 3/4 times 1 is negative 1/4. 1 plus 3/4 times 1 is 7/4. And so my coordinates of R are 1/4, negative 1/4. They'll often ask them for it in coordinate form. And it's going to parentheses for coordinate form. So it can be helpful to end by giving coordinates. Yes. Okay, be aware that while it's given in coordinate form, it can translate into vector form. Make sure you answer in the correct form on the exam. Answer in the form. If they ask you for a point, give it in point form. If they ask you for a vector, give it in vector form. Um, parametric. They can get hard, yeah, but remember we though had equations like x equals 2t plus 7, y equals 3t minus 1, and we never did z, but in vector form, I could write that as the r vector xyz equals 7, -1, 5 plus t 2, 3, 2. Does that kind of make sense?
Oh, so you just. Like, put the, yeah.
7 plus.
See,
Okay. I'm gonna grab the IB formula packet and get it open because I think this is in it.
no. Oh, it's no, it's 2, 2 plus.
And I just moved it around. That makes sense how I got that. And so parametrics almost become unneeded with vector form. So here they're notating it as separate parametrics. So write a parametric equation of a line passing through these. So let's go, we'll start at A and we'll go AB is going to be my change vector. A to B is 4, -1, 1. So X in parametric form is -1 plus 4t. Effectively, we always make our change be a t of 1 or a lambda of 1. 2 plus 1t z equals 0 plus 1t. And so these are my slopes, essentially.
2 plus 1.
Oh, yep. That should be a minus t. That should be plus -1t. Yep. You guys can get started on tomorrow's. Yeah. Yeah, I'm trying not to get it. Does this make sense? So if you're in your IB formula booklet, they have that in there. Mm-hmm. And so it's a pretty simple translation. They probably won't care in most of the problems. Actually, they probably prefer vector form. If you solve for lambda, you get these. which are kind of essentially, yes, T or lambda. So let's see what's actually in the IB formula book. They only give you this version. You can solve them all for lambda. So how they got the other version they had, you're taking, let's do this one. Z equals Z0. That's your initial Z plus lambda N. N was your change in the Z's. So they subtract Z0. And then they divide by lambda. No, not divide by lambda, divide by N. So if you solve them all for lambda, you end up with this. It says they will not specifically ask you for this on the IB exam, but they might in some of the questions, because if you can understand this, it makes any of the questions look easier. Yes, for that particular one. Yeah. Yeah, it's simple algebra. It just looks hard when you see it with all the variables. Yep. So it says the vector equation for the line R is this. Write this equation in Cartesian form. That's just gonna, is that standard? Yes. Yes. Yep. Yeah, no, I hope you feel better. So Cartesian form, I don't feel like going through and figuring that out. So I'm going to go X, I'm going to put it in -2 plus lambda. And then solve X plus 2 equals lambda. I think this is easier. I've tried to do it the other way in the past, and this is translating it into those forms. So Cartesian form is going to look like those. So y minus 1 equals negative lambda. 1 minus y equals lambda. And z minus 3 equals -2 lambda. And then to bring the negative out of the bottom, I'm just going to reverse the top. So Cartesian form is going to look like this. I'm not sure if they wrote those over 1. I think they did, but I'm not sure if they did in the final. Yeah. And that's your Cartesian form of your 3-dimensional line, which is a little weird. But I totally think it's easier to just write these equations and solve for lambda, set them equal, than to try to do this conversion here and memorize those forms. Because the algebra was all simple. Okay, so this is, right, it's vector form. It's going the other way. Again, I think I'm just going to do equals lambda for each one, and then put it back. That's an X. Now, just going backwards, make sure you put them all in the same order. Don't do lambda minus 2, because the vector equation then -1, 1, -2 plus lambda 3, -2, 1. I have the same thing that the answer does. That makes sense. And the last one, find A. If point 2 A plus B is on this line, find A, B. So first thing I'm going to do is find lambda. 1 plus 2 over 3 equals lambda. So I plugged in my 2, lambda's 1. So now I'm going to use that. Y is A equals lambda, so it equals 1. No, you just need to, I don't think that's what I would have done initially either. I'm going to subtract 1. Negative A equals 1. A equals -1. And then 2 plus B over 1 equals 1. 2, B is -1 again. So A and B are both -1. A plus B is -2. Good job making sure to answer the actual question.
Want one answer, then, so that I find a way to.
And they sometimes often will. It's a really good practice for read the question. or as your dad would say, RFQ. Hmm. Okay, so that is vector equations for a line.